welcome back guys to the channel. So in this video we are going to take a look at the EinsteinPy, which is a special package designed for general relativity. Okay, so we are going to start in by knowing what is general relativity. I am going to give a brief glance about this, and for detailed purpose you should go to this general relativity lectures taken by Stanford University professor and all, so you can go through that. So basically general relativity describes the interaction between the geometry of space-time and the energy momentum of the matter. So this is the equation which we are going to define, which we are going to work on. So the Einstein equations are basically a set of coupled partial differential equations of component of metric g mu v, and the metric define the geometry and space-time of the manifold. Okay, on the left hand side we have seen this, and where all of this you can read and can get a gist by going through the lectures. Okay, then only you can learn what we are actually doing. So what does all it all means? Okay, what we are doing, what is the benefit of this, or what is going on. Okay, so the Einstein field equation are the 10 equations contained in the tensor equations shown below. Okay, we are going to show it in the tensor form, which describe the gravity as a result of space-time being curved by mass and energy. Capital G mu v is defined as the curved space of the time at a particular point in space and time, and is equipped with the energy and momentum at that point. Solution to the equation of the component of the matrix tensor G mu v, which we are going to define below, which specifies the space-time geometry. The inertial trajectories of the particle can then found using the geodesic equation. Okay, geodesic equation. Okay, so we are going to start in by importing SymPy for simple representation and EinsteinPy of course for general relativity. First you have to install it on your disk, then you can use it by importing it into your lab. So let's calculate the behavior of scalar factor of the universe. So this is that the Einstein equation predicts. So for Einstein equation, it has predicted a it works for a homogeneous and isotropic universe filled with a perfect fluid. So first we are going to define this symbol G naught naught and all raw and all. We are defined it as we have seen in the first equation. So we are also using SMP dot equation, which is going to convert it the following expression into an equation. So we are not taking a polynomial, actually we are taking an equation. So we are using this new function called equation. Okay, in the basic series of SymPy you can find it. Okay, part 1. Okay, in SymPy you can find it. So after this we have defined the energy momentum tensor for a particular fluid. So energy momentum T naught comma mu rho. So we have defined it T naught equals to rho, and we have defined some additional symbols for time and position in x and y. So okay, position and this, and also we have used the SymPy dot function for defining a scalar factor. Okay, this special. So after that, the line equation of an homogeneous and an isotropic universe with no curvature is described by this equation. So we are going to describe this because these are the this is the very basic, this is a very basic thing in cosmology you are going to encounter in few 1 or 2 lectures. Okay, in the first 1 or 2 lectures, and it lasts forever because this is very important how we are going to define the space around us. Okay, it may be we have to define it for 2D 3D flat and all. We can define it by these type of equations. Okay, we are going to use it. So after that we are going to import Einstein tensor and matrix tensor from EinsteinPy dot symbolic, and we are going to define a M matrix which has the diagonal elements like this and as described, and matrix will be a metric tensor, and this is the final metric that we are going to get from M. Okay, so this is the final matrix. So after that we have used this Einstein tensor from matrix, and given the value for matrix we have transforming the matrix that we have get above. So this gives us the final matrix on which we can perform our processor our project. Okay, so for this we have also defined the Hubble constant, which gives us the relative velocity of expansion of AT for this respect. Because we are talking about the universe, so we have to take Hubble constant, it is very important. So Hubble constant, this A naught represents the differentiation of A. So if I'm going to describe the HT, So it is going to take the SymPy equation module and then going to give me this h equals to differentiation of 80 divided by 80. So this is the Hubble's constant, and then we are going to describe it for g naught naught, and hence we are going to get at the final, we are going to get 3h square equals to g pi g rho 8 pi, sorry, 8 pi g rho 3h square 8 pi g rho. So these are the basics for Einstein pi, and hope you like this video. And in the coming videos we are going to do some good projects related to general relativity, because I'm too learning this concept, and due to my curiosity I went on to write some good code, but still I have to learn a lot to make some notable contribution to do some good work, some good projects. I have to learn it. So maybe in 1 month I'll be delivering a next video on Einstein pi, and particularly on general relativity, and we'll do some good concepts related to it. So yeah, that's all for this video. Hope you like this video. So see you again next one. Thank you.